ground. Okay, this trash is removed. Originally, balance the ground embedded at D in this location. The geostatic stress equal gamma Z. But when we calculate the foundation peak, the stress decreases to 0. That means some load removed. Okay? So when the superstructure built, the load increase. But when the load not reaching the load removed, it cannot produce the stress increase. Only when the load equal or more than the load removed, the stress increase produce or increase too. Okay, so here we use the net pressure, not the total pressure, to calculate the vertical stress increase. And the net pressure equals the total pressure divided by the gamma D. Okay, the geostatic pressures at the depth of embedment. Okay. Here, pressure increase P0 should be introduced here rather than contact the action. We use the pressure increase for calculation of the stress increase, not use the contact pressure. Okay. And finally, we should discuss a principle of effective stress. What effective stress? How about principle of effective stress? First, we know the soil is composed of soil particles. We call soil particles, and water or gas or air in void. Okay. So when the load applied to the soil, the load is carried by soil particle, and the water or air. Okay, but for saturated soil, no air in void. Okay, the void is full. It's filled with water, no air in void. So the external force called the total pressure. Okay, the total pressures include two parts of. One for carried by soil particle, soil carried others carried by the pool water, okay, water in void. So total pressure is sustained by both skeleton and the fluid. What the ratio of pressure sustained by soil, skeleton, and fluid, or how pressure transferred to soil, skeleton, and fluid in void, and what are the influence to deformation and the strength of soil? Maybe the three problems related to the principle of effective stress. Okay? Maybe deformation.
Is it deformation?
Deformation.
Deformation.
Yes. Not formation. Deformation.
She said deformation, right? This one, right?
Deformation and strength. Okay. Maybe deformation. Formation. Formation? Not formation.
Here we can change it.
Deformation and strength. Okay. Here we should analyze the total pressures, how total pressure transfer, and how total pressure sustained by soil, skeleton, and fluid. Okay. Here we take a section through the contact point of the particle, like this, section A. Section A through contact of particle, maybe a not plane section, but a curved section. Okay. Here we use A. We create that cross section area. A as contact area, and A that area of fluid, area of water. So the cross section area equal AS plus AW. Okay, and the sigma times A, the total node, equal the node carried by the soil particle and the node carried by the pool water. Okay, so we can derive this equation. Stress on section A plane or horizontal plane. soil particle unknown carried by pore water. Here, sigma p as we represent the total node vertical, the total vertical node carried by soil particle. Maybe node transmitted through the contact of soil particles. Okay, node transmitted through contact of soil particle. Here, in this equation, maybe the A W equal A. For the AS is very small, equal 0. The contact pressure, contact area is very small. So we assume the area of water, for water, equal the cross-section area. So the equation, this equation, we can rewrite to the effective stress plus the pore water pressure. Okay, this is the equation. Of the effective stress principle of effective stress. Here, sigma is effective stress. It means the stress carried by the soil particle, okay, transmitted through the contact of soil particle. Maybe absolute values here divided by A cross-section area. So maybe the effective stress, not the real contact pressure, but the absolute contact pressures. Okay, and represent the pore water pressures. Okay, in this equation, the pore water pressure have no effect on the deformation and the strength of soil, because the pore water pressures cannot make the soil particle move. So it has no effect to the deformation or the strength of the particles. Here, effective stress is the mainly reason for the soil deformation or soil failures, soil strength. Okay. So in saturated soil, we use the effective stress to calculate the the deformation or the settlement or the strength of the soil. We've discussed a case about lowering groundwater. Okay, when groundwater level decreases, the effective geostatic pressures may increase. Okay, like this, the original groundwater level, and it decreases to this location. Okay, and the effective overburden pressures for original groundwater level equal this value. When the groundwater level decreases to this location, the effective overburden pressures will increase this area in the increase of the effective overburden pressure. Okay, for this soil nest, originally below the groundwater level, we use beyond unit weight calculation. But when the groundwater decrease